Welcome to the first progress check help videos. We're going to be going through the top 10 most missed questions on the progress check and try to give you a better understanding about how to do the corrections to those or just give you some tips and ideas about how to solve those types of problems. So unfortunately we can't go through every single question, but we will try to cover the top 10 that were missed most often for progress check part A. We'll be covering number 3, 6, 7, 8, and 9, 12, 14, 16, 18, and 20. Let's go ahead and get started with number 3. I think the biggest issue on this one was a lot of people just kind of assume that we're still talking about a torque versus alpha graph like we did in class. And when we graphed those, we got that the slope was the moment of inertia. But if you look carefully at the way they describe this, it says that they create a graph of the door's angular acceleration as a function of the net torque. So they actually have their axes reversed. And if you were to do that, then when you graph it this way, your slope would be the exact opposite of that idea of moment of inertia. It'd be 1 over the I value. So if they were to graph this, you'd have to take the inverse of the slope, and that would get you your moment of inertia. All right, number 6 becomes a kinematics problem. What they're doing is they're asking you for the angular displacement, and they give you a graph of this acceleration. It looks like a very constant positive 6 radians per second squared. And that it matters that it's positive because in the problem they give you this initial velocity that's clockwise, and that would be technically a negative value. So this acceleration is working opposite of this value here. And we'll keep track of that in how we lay out our math. So the way I organize it is I write out the variables that my knowns and my unknowns. And as far as known values, I know that the alpha is a positive 6 radians per second squared. I know that the time is going to be 10 seconds. And I know that the initial omega is a negative 3 radians per second. And again, the reason I'm putting that as negative is because they say in the problem that it is clockwise, and clockwise is negative, whereas our graph of acceleration shows a positive 6 radians per second squared. For the unknowns, I'm looking for delta theta. I don't know how fast it's going to be going, the final angular velocity, but all I really need is the angular displacement. So I don't need to solve for omega final, but you could write it out. All right, so then we go to pick our kinematics equation, and you see if I'm looking for delta theta, that's the thing that I'm trying to find. It's in 2 different formulas, so either one of these might be a good choice. But then if you look at your other unknowns, I don't know omega final. And so if I don't know this and I don't know this, that's not going to be very good for solving. That's 2 unknowns in the same equation. So I'm going to be steered towards this equation and just kind of going through making sure I have everything. I know the alpha value, I know the time, I know the starting velocity. So I have everything I need to solve that formula. So delta theta equals 1/2 times the value of 6, positive 6 radians per second squared, times the time of 10 seconds squared. And then we're going to add that to a negative 3 for the initial velocity times 10. So I end up with like negative 30 here. 10 squared is 100, times 3 is 300. And so the total is 300 minus 30, or 270 radians of displacement. All right, in number 7, we had this particle Z, this piece of clay that was traveling straight in at a board, and we were supposed to rank what happens with linear momentum and angular momentum. Well, I think angular momentum is the easiest one to talk about first because angular momentum involves this rotation about an axis, and Z is going to be going straight into that plane. That pathway would be straight along the line of action here. So it's not going to provide any torque. It's not going to spin the beam at all. And therefore, there's 0 angular acceleration before impact, and after impact there'd be zero acceleration also. So there's no change in the angular momentum. And again, because they said they're talking about the clay and rod system, then it's conserved. But linear momentum goes down, and the reason for that is that this thing has some mv to it to begin with, so the initial momentum of that system is to the left, and when this collides and sticks, it's not going to be moving at all. And the reason for that is because it is bound in place by this pin. This pin is an external force that prevents the stick from moving to the left to conserve the linear momentum. So the linear momentum is not conserved, and it actually would decrease as a result of this collision. This is a pretty challenging problem for the derivation, but what it comes down to is this particle y, piece of clay that's going to smack into the board right at this length, lowercase l, is going to make this whole thing start to swing with angular momentum. And in fact, it moving on its own is having its own angular momentum relative to this pivot point, because that is motion perpendicular in some aspect to this pivot point here. So the clay actually has angular momentum even though it's moving in a straight line, because we're referencing it from this pivot point here. Back in the last problem, Z had no angular momentum because it was moving parallel to the line of action with the pivot point and had no perpendicular motion relative to that. But because Y has perpendicular motion relative to this axis of pivot, it can be considered to have angular momentum. So the way this works is we're going to conserve angular momentum. The L of the system equals the L of the clay plus the L of the rod. And beforehand, the rod isn't moving, so there is no angular momentum of the rod. It's not spinning at all, but the piece of clay moving at this exact length, lowercase l, away, can be written with angular momentum. So the way that looks is the L of the system, or just the angular momentum of the clay, is the moment of inertia of the clay times the angular velocity of the clay. And that would be its little mass of the clay times that radius squared, which is lowercase l, times its initial omega, which they define as just, let's see. Oh, you know what? Instead of using omega, omega is just v divided by r. So I would just substitute in that if it's moving at a speed v initial, and the length away that would be discussed would be L. So this breaks down to having the total angular momentum, okay, L of the system, would just equal the mass of the clay times the velocity initial of the clay times the radius that the clay is going to smack into, which we're going to call lowercase l. So that is technically both of these things added together. That's the clay and the rod. We just so happened that the rod was 0 to begin with, so all of that system's momentum should be equal to this. So after they collide, we still have to have the same total L of our system. And so now the rod and the clay will be rotating together with some final angular velocity, but the fact is it still has to get you back to this total value that is here. So when we write the after condition, after they impact each other, this L of the system, which is m sub c v initial times length, that product has to equal the I omega of the clay plus the I omega of the rod. And so we'll just write out those together. Well, the I omega of the clay is the mass of the clay times length squared times omega final. That's this part here is its moment of inertia. That's its I value, mass times radius squared. For just a blob of mass sitting at an exact radius away, this is just the generic form of it. It's just mass times radius squared. Keep in mind I'm just substituting L in for radius because it's the variable that they defined. Then I'd have to multiply that by the omega final of the clay, which is, we'll just call omega final. Then I'm going to add that to the I of the rod, which they just defined as I of the rod, times the omega final as well. Well, I look across those terms and I have omega final in each, and so omega final multiplied by the mass of the clay times length squared plus the I of the rod would equal this MCVO times L. So ultimately, if I solve for omega final, I'm going to divide by all this stuff. And so divide each side by MCL squared plus I rod. And you get this expression, which is the correct answer given here. All right, so sorry, the picture's a little out of place from where it is on your guys' view, but on this one, you're supposed to predict which way this rod will swing, and there's no other resistive forces, and they're all going to hit at the same time. So you got clay Z smacking straight in. Well, that's not going to cause any rotation, so it's just going to lump onto the end here and not rotate it at all. Clay Y is going to smack here and try to make the thing swing clockwise, and clay X is going to try to make the rod swing counterclockwise. Well, clay Y is going to dominate this interaction because it's going to provide the most torque. Since they're all going the same speed and they're going to collide at the same time, they're going to provide equal amounts of force when they smack into it, but it has the largest radius away. And so if you have the biggest radius, you're going to have the most torque, and if it has the most torque, that should dominate the interaction and make this thing swing clockwise. So A is the correct choice because it says it'll make it swing clockwise in a constant angular speed. And the only other one that I think people would be going with is this clockwise with a changing angular speed, and they might have thought like it'll slow down over time or something like that. But because this is, it's all going to collide and stick, and it's a frictionless environment, no other competing forces, this will just stay swinging around in this new orientation. All right, I think this one's, number 12, is the easiest to understand if you think about this motion graphically and break it up into its two parts. There's really two types of motion taking place. There's an accelerated motion for a first time interval from time of 0 to time of t initial, and then it's going to spin at a constant angular speed, meaning there is no net torque. There's no acceleration for the second part from the t0 to t1. And they want to know what the total displacement is from the beginning of time 0, all the way to time 1. And you have to express your answers in all of their terms. So if I just graph this out off to the side, you're going to have this initial omega that you're starting out with, and because you're accelerating, you're going to be changing your velocity. We're going to assume that it's speeding up. I don't know if it matters too much in this problem because we don't have any real numbers. But I'm going to accelerate until this t equals 0. Then I'm going to go at the steady, constant velocity, angular velocity, until this t1. So really, when they're asking for displacement of angle is just the area under curve for a omega time graph. It's the same thing as true that displacement x was the area under the curve of a VT graph. Well, all of this area is...
Sorry, we've been interrupted by Grace. Boop, doop, 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 doop. She's really excited about me making more physics videos. Yay! Clap, clap, clap. Okay, say goodbye. Bye-bye. Study hard.
All right, so finding those areas, if we just focus on this first section here, that represents a certain amount of displacement given by how it's moving with that accelerated motion. So we could write out that formula. That would be the change in theta for that first time interval is equal to 1/2 alpha times the time that's going to go is at t initial squared, plus the starting velocity, omega initial, times that same exact time value, t initial. So that has to be part of our answer. Like that's some of the displacement is this amount right here. Whoops, try that again. Is that coming from that first green shaded section. Then to get this other section, this rectangle here, we'd have to know the value of velocity that it's traveling. That would be like this. Let's switch pens here. That would be this value right up here. And so I don't really have a value for omega final, but I could express it using my equation. Omega final after a certain amount of time has gone by would equal omega initial plus alpha, and that t that's gone by would be, to get up to that point would be t0. So that would explain how fast it's going after this much time has gone by. So now it's like I have a value of this maximum height, and I know that the length here is to to t1. So then I can just do length times width, and we'll say the length would be this like omega final, omega initial plus alpha t initial times the x-axis here, which would be t1. So that's your second value of displacement. So if you just add those two together, the blue square and the green trapezoid, that would be your full expression, and that's what you see in the answers for part D. All right, this particular problem is a good reminder that every time we hear change in L, we are thinking of graphically how you can get it. It's a torque versus time graph, the area under the curve. And in this case, we weren't given torque, but we're giving force versus time graph. So what you'll often see is anytime they talk about change in L, if they don't give you a torque versus time graph, they typically give you a force versus time graph. And then because they gave us information about the radius in the problem, we can take that force multiplied by radius to actually get back to torque. So that fundamental theorem, that's the impulse momentum theorem, the change in L is equal to the net torque times the amount of time. This is almost identical to what we had in the momentum section where we said the change in momentum equals force times time. It's just phrased with angular properties. So if I want to take they say the vertical intercept, so like the net force here was about 3 newtons. So if I take 3 newtons times the radius of 0.25 meters, they give us the diameter, so we have to do a little math there. Take 3 newtons times 0.25 meters, that value is the net torque. And if I do that over the course of 8 seconds, times that by 8 seconds, I'm going to have the exact value of the change in L, or the change in angular momentum. I was honestly a little surprised that number 16 showed up as one of the most missed questions. It seems to be a pretty straightforward torque problem, so let's just go through that. Maybe there was some misconceptions about how to solve or where to solve from, but it says about its center, what is the magnitude of torque exerted on the rod about its center, meaning like the center would be the pivot point. So if that's our pivot point, then this 20 Newton force here exerts no torque on the object. So you can just kind of cross that out. That doesn't really matter. Well, up here, you have 20 newtons of force pulling to the right. So friction, if this is not going to slide, friction would produce an equal amount of force of 20 newtons back. And so, let's see, 20 newtons of force times the radius of 0.5 would give you 10 newton meters of torque, trying to make this thing swing that way. would be the direction. We do the same thing down here, and you got 20 newtons of force pulling that way, so that must mean there's 20 newtons of frictional force pulling back. Keep in mind what we're actually calculating is the frictional force that's opposing these poles that they drew in the problem. Well, that would be, again, the same exact calculation. Torque equals 20 newtons times a radius of 0.5 meters, and that would equal 10 newton meters. You see how that's actually in the same direction. If this is our beam, both of these are working together, trying to make this swing counterclockwise. So that's a 20 newton meters worth of torque if you add them both together. 10 newton meters counterclockwise plus another 10 newton meters counterclockwise, and this thing will, well, it won't spin due to the problem, but that's which way the net torque is trying to make it spin. All right, they said change in angular momentum on number 18, so again, we need to kind of get in the habit. Anytime they say delta L, to change in angular momentum, the only way you can do that is to provide a net amount of torque for a certain amount of time. Well, in this one, we know the amount of time that's given to us. So that variable, we don't need a stopwatch or anything to calculate that. But they do show all these forces that are drawn in the problem, F1, F2, F3. And so we would have to know how much force is being delivered. And so the only other thing we need to know for to calculate torque is if we know how much force, oops, let me switch pens. If we know how much force is being delivered with the force probe, and we already know what radius it's at, then we just need to know what angle, this equation FR sine theta, we just need to know what angle those are being pulled from. That will get us our torque. And Grace is not happy with these solutions, so I might just do this last one and then we'll call it good. All right, last one, number 20, talks about whether or not a student's claim is justified by saying that the frictional torque is independent of the wheel's angular speed. And this is a little confusing. Like, how would you know? First of all, you have to understand what that phrase is talking about, and then how are you supposed to just tell off this graph if that's true? Well, the student's claiming that the wheel's friction, like this is just be like a wheel, even like the ones that we had in class that were spinning around. There's probably be some friction in the central hub as it's rotating. And so as this thing's spinning around this way, it's going to feel some friction to slow it down naturally. And so that slope that you get, it's really, really constant. And that indicates that as this thing is slowing down, we're not getting different amounts of torque acting on the wheel. If this started to like change as the momentum went down and the slope started changing, then you could make a claim for that the friction was dependent on how fast the wheel was spinning. But even when the wheel slows down like half of its original value, the slope stays consistent throughout that whole trend. So skills needed in this one are you have to know what is causing a change in angular momentum, so there must be a torque. This is actually the third or fourth time this idea has come up, I think, on these checks, that to change the angular momentum, a net torque has to be applied. And if this torque coming from friction, force of friction acting at some radius away from the hub, if that was dependent on how fast it was going, you would see the slope of this line change as the function went on for 10 seconds. But the fact that it stayed consistent in its slope means the change of momentum was constant, meaning the torque was independent of that value. And that's going to do it for the first progress check A. I will attempt to make a progress check B for topic 7. Stay tuned for that.